Hey everybody, so these are the solutions to the worksheet 2.3 on quadratic functions. In number 1, we've got a quadratic function 2x squared minus 4x minus 1, and we're asked a few things. So first we're asked to find the x and y intercepts of the graph if they happen to exist, which they may or may not. So let's start with the easier of the two, which would be the y-intercept. So we know that the most straightforward way to go ahead and calculate the y-intercept is to take our function f of x, and we're going to go ahead and we're going to evaluate it at 0. So this is going to give us our y-intercept. And if we do that, we'd have 2, 0 squared, minus 4 times 0, minus 1, which is just going to give us a value of minus 1. So there's our y-intercept. That's where it's going to intersect the y-axis. Okay, so next, let's try the x-axis. So to find the x-intercepts, what we're going to do is we're going to take our function, 2x squared minus 4x minus 1, and if we ever want to find any, see if there are x-intercepts of a function, we just set it equal to 0, and then we can solve this for x. Now with quadratics, we could see if it factors. In this particular case, though, it's not going to factor out nicely for us, so we use our fallback, which is the quadratic formula. So let's go ahead and set that up. So we know that if we identify a, that's our lead term, which is 2, our b is going to be equal to negative 4, and our c is equal to negative 1. And what we're going to do is we're going to use these values in the quadratic formula, which tells us that the solution x is going to be equal to minus b plus or minus the square root of b squared minus 4 times a times c, and then all of this divided by 2 times a. All right, so let's go ahead and apply this to this case. So x is going to be equal to minus b plus or minus the square root of b squared minus 4 times a times c. It's all under the square root. And then we're going to divide that by 2 times a, which in this case is also 2. So let's go ahead and clean this up and see what we get. So we're going to get 4 plus or minus square root. So minus 4 squared is going to be 16. And we have minus 4 times 2 times minus 1, so that's going to be plus 8. And then that's all over 4. So that's going to give us 4 plus or minus the square root of 24 divided by 4. So these are our two x-intercepts. We can do a little bit to simplify here to make this look a little nicer, so let's go ahead and do that. We can simplify this radical. I'm going to do the simplification of this radical up here. So let's say we've got the square root of 24. If we suspect that we can simplify a radical, we can think about it this way. 24, if we were to factor it, is 4 times 6, and since we're allowed to break up radicals with multiplication or division like this, so we can say, well, the square root of 4 times 6 is the same as the square root of 4 times the square root of 6. We can now simplify the square root of 4 as 2 times the square root of 6. So we could simplify that if we were inclined. And usually you're asked to simplify, so it's probably a good idea. So we've got 4 plus or minus 2 times the square root of 6 all over 4. And we can do a little bit more here. I'm going to bring this up here now. So what I'm going to do is I'm going to factor out a 2 out of the top and the bottom. So if I do that, I'm going to pull 2 out of, which would leave me 2 plus or minus the square root of 6. So 2 is a factor of the top. 2 is also a factor of the bottom. So these 2's, since they're factors of the top and the bottom, are going to cancel. And we're left with 2 plus or minus the square root of 6 over 2. And while it might be tempting to want to cancel those 2's, we can't do that. What we will want to do, though, is we could break this up as 2 over 2 plus or minus the square root of 6 over 2, which will simplify to 1 plus or minus the square root of 6 divided by 2. So these are our two x-intercepts. for this quadratic. You can see a lot of the work that we had to do here was really just a simplification, so do be careful with that if you come across it. Okay, so let's go to part B now. So we were asked to convert this function into standard form. Now what we've got here, by the way, this is what we call the general form, or at least the text will refer to as the general form of a quadratic, but now we're being asked to work with the standard form. Standard form looks like this. It's going to be f of x is equal to a times x minus h squared plus k. Where if we took that h and that k and made it a coordinate, so where the point h, k is the vertex. So we've got that going for us. So if we know h and k, or if we know the vertex and we know this this term a, which we've actually got from part A right there, that still remains the same. It's that lead coefficient. Then we can go ahead and we get standard form. So what I'm going to do is I'm actually going to put this one on hold, and let's do part C first, because part C actually asks us to find the vertex. So if we can find the vertex in part C, then we can go ahead and we can use it to finish part B. Okay, so if we wanted to identify the vertex, one way to do this is to use the vertex formula. This allows us to take any quadratic and then identify the vertex. So vertex formula tells us this. So given the general form of a quadratic, meaning f of x is equal to ax squared plus bx plus c, then the vertex is the point, and this takes a little bit of calculation, but is going to be the point minus b divided by 2a. So we take our a and our b, and we get the x coordinate of the vertex. And then to get the y coordinate, what we're going to do is we're just going to take the function and evaluate it at that x coordinate, minus b over 2a. So we can calculate the vertex, and this will then give us the point that we were looking for, hk, which we can then use back up here. So let's go ahead and make this quick calculation. So we'll start with the minus b over 2a part. So we know from part A that b is negative 4. So we've got minus b divided by 2 times our a, which is also 2. So this is going to end up being positive 4 over 4, or just positive 1. So this is going to be our h. This is the x coordinate of our vertex. So to get the y coordinate, we're just going to go ahead and take our function, and we're going to evaluate it at minus b over 2a. In this particular case, that means just evaluating our function at 1. And that's going to give us 2 times 1 squared. So this is just from the function they gave us at the start of the problem. Minus 4 times 1 minus 1. So we've got 2 minus 4 minus 1, which is just going to give us negative 3. And this is our k. So from this information, we now know that our vertex is going to be equal to the point 1, negative 3. Now, there are other ways to find the vertex. You could use you could actually use completing the square to put it in standard form first, and then get the vertex from there. Calculator also, as we'll talk about later, has the ability to use that, but oftentimes you're going to be asked to do this by hand, so we'll want to know how to do this. Vertex formula is a nice, easy way to do it. Okay, so now that we've got the vertex, let's go back up to part B here and consider that since the vertex hk is the point 1 minus 3, and since our a in this case is equal to 2, and again, just in case we don't remember where that came from, the a came directly as our lead coefficient from the general form. So the a of the general form is the same as the a of the standard form. So since we have these two, we can now put together our standard form using the generalization here. So we've got f of x is going to be equal to a, which is 2, times x minus h, our h is 1, squared, plus our k, which in this case is negative 3. And when the dust settles here, we've just got that f of x is equal to 2 times x minus 1 squared minus 3, and that would be the standard form of our quadratic here. Okay, so now we'll go down to our last question, and this asks us to identify the axis of symmetry. Now, axis of symmetry refers to, we know that quadratics look like parabolas, and they're symmetric from left and right. It's got that sort of vertical symmetry going on. So the axis of symmetry sort of defines the line that cuts that in half. In general, what we say with quadratics and the axis of symmetry is that the axis of symmetry is always going to be equal to the line x equals h, where h is that point, the x-coordinate of our vertex. So we've got a vertical line going through the vertex, and we would name it as x is equal to h. So in this particular case, we see that the axis of symmetry is going to be the line x is equal to 1. So if we were to draw our parabola and then draw the line, a vertical line, x is equal to 1, it would be cutting that parabola right in half. And we'll see that with the next one when we actually have to graph it. Okay, so if we move on to number 2, what we see here is that now we still have a quadratic function, but this is actually given to us in standard form. So we can look at this, and just right off the bat, it's probably a good idea to start taking note of these characteristics. So we know that this is in standard form, and we know a few things already. We know that our a is this coefficient from here, which is basically just negative 1. Our h is a number that we're subtracting from x, so it's got x plus 2. In this case, our h is going to be minus 2, the opposite, and our k is going to be equal to negative 3. So we've got some really good information already that we're going to see that we'll use later on in this problem. Okay, but first they're asking us to find the x and y intercepts. So let's go ahead and we'll start with the y-intercept. This is old hat. We've done this dozens of times at this point probably. So find the y-intercept, we just find f of 0, which in this case is going to be negative 0 plus 2 squared minus 3. We just took our function and we plugged in 0 for x. This is going to give us minus 2 squared minus 3, which will give us minus 4 minus 3, which gives us y is equal to negative 7. So there's our y-intercept. It's going to hit the y-axis at negative 7. Let's go ahead now and we'll do the x-intercept. So we know to find the x-intercepts, if they exist, what we do is we take our function, minus x plus 2 squared minus 3, and we're going to set it equal to 0, and then solve for x. Okay, because the real solutions to this equation represent our x-intercepts. Now you could do this a couple different ways. You could multiply it out, use the quadratic formula, or we could leave it in this form and utilize the square root property to help us solve this. So what I'm going to do is I'm actually going to add 3 to both sides first. So this is one way you could do it. If I add 3 to both sides, and then I'm going to next multiply both sides by negative 1 to get rid of that negative sign. So that's going to give me x plus 2 quantity squared is equal to negative 3. Now to get at that x, I'm going to have to take the square root of both sides. So if I take the square root of this side and the square root of this side, I get x plus 2 is equal to plus or minus the square root of negative 3. Now this should not sit well with you all, because we know that in terms of real numbers, we can't take the square root of a negative or the even root of a negative number. So what we see here is there's actually no real solutions here. And since there's no real solutions, to this equation, this tells us that there are no x-intercepts. And we'll see what that looks like when we get to the bottom to graph it. But it just means that the curve doesn't hit the x-axis. It doesn't necessarily have to for quadratics. Okay, so for part B, what we're going to do is we're asked to convert what we have a function in standard form into general form. And as a reminder, general form is going to look like this. F of x is equal to ax squared plus bx plus c. Essentially all we need to do is multiply out the standard form, collect like terms, and get it into the general form. So let's just go ahead and do that. So if we multiply out our multiply it out. If we multiply out the standard form, this is what we'll get. So we've got f of x is equals to minus quantity x plus 2 squared minus 3. So first thing we'll do is we'll square this. So we'll have minus, and if we multiply x plus 2 times x plus 2, we get x squared plus 4x plus 4 minus 3. Distribute that negative, we have minus x squared minus 4x minus 4 minus 3, and what we see is that our general form will be f of x is equal to minus x squared minus 4x, and then we add those two constant terms to get negative 7. So this is going to be the general form of this quadratic that we're working with here. Okay, so for part C, we're asked to find the domain and range of the function. Well, one of the nice things about quadratics, which they're part of a larger family of functions called polynomials, is that the domain of any quadratic will be all real numbers. So the domain of any quadratic will be all real numbers. So we could go ahead and we could write this as just saying, well, this is going to be the interval from negative infinity to positive infinity. So this represents the domain. And for the range, so the range, it's probably going to be good. Let's wait on the range for a second. I think once we get down to the graph, we'll be able to kind of see this. You might be able to figure out what it is, but let's hold off. It might be a little more clear when we see the graph. Okay, so we need to identify the vertex. Well, luckily we know that the vertex is the point hk, given standard form. And if you remember, I'm just going to scroll back up here. We've got standard form. We know that h is -2 and k is -3. So in this case, it's the point -2, -3. So we got that from standard form. So there's our vertex. And we also know that the axis of symmetry is the line x equals h. So in our case here, it's going to be the line x is equal to -2. So by identifying the a, the x, and the h from the get-go, it kind of made these problems a lot easier. And for part F, we want to determine whether the vertex yields a relative and absolute maximum or minimum. And whether or not this vertex does yield a max or a min is going to depend on in which direction our parabola is oriented. So, for example, if we have a parabola that is facing downwards, like this, then we know that the vertex will serve as the maximum value. Whereas if we have a vertex that is opening upwards or concave up, or a parabola is concave up, then our vertex is going to be at the bottom, so it would be a minimum. So determining whether our parabola is concave up or concave down will let us make this decision. And what we look to is the lead coefficient to make this determination. So we know that if our A is positive, then this means that our parabola is concave up. It means that it opens upwards like this one. Whereas if our A, our lead coefficient, is negative, then it is going to be concave down. like this one. Now, in our case, we know that our a value was equal to -1. So since it's negative, this implies, so since a is negative, we can conclude that our parabola is concave down. So the vertex is a max. So it's going to be kind of like this one right here. We're going to graph it to see. But since our parabola is concave down, we know that the vertex has to be a maximum point. Okay, so let's actually go ahead and show that for sure. So we're going to go ahead and we're going to graph f of x. So we've got plenty of information now to get this accomplished. So I'm going to draw my axes here. So here's our x-axis and our y-axis. And let's go review what we've got. So we know that we've got a y-intercept at -7, no x-intercepts. We've got a vertex at -2, -3, and it's going to be a concave down parabola. So let's go ahead and put all that information together. So if we go down to, let's plot the vertex first. So -1, -2, and we're going to go -1, -2, -3. So this will be our vertex right here. And then we'll go ahead and plot our y-intercept, which would be -4, -5, -6, -7. So here is our y-intercept. We also know that we have an axis of symmetry through the line x is equal to 2, so our parabola is going to be symmetric across that. And we kind of know what parabolas look like. It's going to be concave down, so we're going to have something that kind of looks like this. It's going to swoop down, it's going to hit the y-intercept, and then it's going to be symmetric across this side as well. So that's a rough sketch of our parabola. Now, one thing that we had kind of left open was the idea of the range. And once we've got the vertex, we determined how the parabola is oriented, it's a little bit easier to see the range. And again, the range is going to be this y-axis projection. So if we were to take a look at this and project our curve on the y-axis, then from -3 all the way down here to negative infinity, that's going to be our range. So the follow-up to, what problem was that? So that was part C. The range is going to be from -3, actually we're going to go from -infinity up to -3, and we're going to include that. So that would be our range in this case. Okay, so let's go ahead and move on to number 3. Number 3 is a fun little word problem here, and we're told that we've got. Let's just kind of sketch it up here. So we're told that we've got these 14 inches of string, and we want to take this and kind of create a rectangular area, but we want to maximize this area of a rectangle that we're going to draw. So just kind of put it over here. We'd like to create some sort of a rectangular area with this string. So kind of bend it around all 4 corners, but we want to maximize this. Okay, so let's go through, we break it down into steps here. So we're going to let, if we think about this rectangle, it's got some length, we could call that L, and it's got some width. It's got a length here, and it's got a width here. So this is sort of a general rectangle. And we're going to let X be the width here. So I'm going to go ahead and say that's going to be X. So what does the length have to be in terms of X? Well, we could think about it this way. We know that if we added up the 2 lengths and the 2 widths, so if we took the 2 lengths and added the 2 widths, this has to be the total 14 inches of string that we're dealing with, because we're wrapping it around to get a full rectangle. Now, we've determined to let the width be X, so we've got 2L to X is equal to 14, and we want to find the length, so let's just go ahead and solve this for L. I'm going to go ahead and I'm going to subtract 2x from both sides, so we get 14 minus 2x. If we divide both sides by 2, then we're going to end up with L is equal to 7 minus x. So this is the length in terms of x. So now we've got the width in terms of x, we've got the length in terms of x. So now we can create a formula or a quadratic function that represents the area of this rectangle, because we know that area is equal to length times width for a rectangle. And in this particular case, our area, which is now going to be a function of x, is going to be equal to the length, which is 7 minus x, times the width, which is x. If we were to multiply this out, we'd get 7x minus x squared. And if we needed to, we could rearrange this and have minus x squared plus 7x. Doesn't really matter, but however you want to think about it. Okay, so this is our area function. So we could pick any x value, plug it in here, and it would give us the area. So we want to maximize this function to find the maximum area. Now here in part C, we're instructed to use our calculator to graph the area function and then identify the parabola, the vertex of the parabola. I don't have my calculator here. I'm sure you've talked about this in class on how to use the calculator to find your max. You go to the calculate menu, you pick max after you've graphed it, and you locate it. Just in case your batteries die and you guys aren't left hanging, this is how we would go ahead and find the vertex by hand. We know that the vertex is going to be equal to, we can use the vertex formula. So if we use the vertex formula, let's try spelling that correctly. So formula. And in doing so, we would first calculate minus b divided by 2 times a. We look up here, our b is 7, our a is -1. So we've got minus 7 over 2 times -1, which is going to give us positive 7/2. This is basically 3.5. Which represents sort of the x coordinate of our vertex. More specifically here, this is our width. And if we wanted to find the y coordinate, we take our function, which is an area function, we plug in the minus b over 2a, and that means we're going to find a of 7/2. If we do this, I'll spare you sort of all the calculations, since you've probably already gotten this from your calculator, but what you end up getting is 49/4, which is 12.25. So if you use your calculator and you got 7/2 or 3.5 and 12.25, then you did this correctly. So this is the y coordinate of our vertex, or the area, because this is what we're getting here, the function. So just as a summary here, our vertex is going to be equal to the point 3.5, 12.25, and that's a decimal in there. Okay, so for part D, what is the y value of the point? Well, we know that the y value is 12.25. And this represents our largest area. So when the width is 3.5, the area is 12.25, and we've maximized it because it's that vertex of our graph. So this tells us that the max area is equal to 12.25 square inches. In part E, we're asked, what is the x value of this point? Well, the x value is 3.5. And this tells us that this is the width at which the max area will occur. Specifically, this will be 3.5 inches. And then lastly, we know what the width dimension of this rectangle to get a maximum area would be. What about the length? Well, we know from up here that length, using this formula, that length is equal to 7 minus x. So L is equal to 7 minus x. In this case, our x is 3.5 that we're going to use. So this is going to be equal to 3.5. So if we use a rectangle with a width of 3.5 and a length of 3.5, we are going to maximize our area. Well, what we have here is we have a square. So in this case, we recognize that a square is going to be the best way to maximize the area of any rectangle in this particular case. Okay, so that will do it, and I will see you all in the next video.